Hi everyone, Mr. Lee here. In this video, we're going to go over two charged parallel plates. Alright, let's begin. Okay, so the first thing we need to cover is this idea of two charged parallel plates. So what that means is we just have some metallic plate that is conductive and it is what we call infinitely long. Alright, so I'm going to draw it like so. We have a plate and we have a plate, hence the title, two charged parallel plates. Now, just so you know, for the sake of us just discussing things and the electric field lines, we say these do go towards infinity. And what we're looking at is we're just taking a look at a section. And that is because of what we are going to describe the field lines as. So let's say the top plate is all positive. Okay, so these are positive plates, and on the bottom we have negative plates. Now I use the word plural there, but it should just be a positive plate and a negative plate. All right, so the next thing that we're going to do is we're going to create our field lines. Now I'm going to show you two different versions. Okay, the first version will be what we are dealing with here, a infinitely long plate or a section of a plate. We will have the top plate have a field line pointing down like so, because remember, field lines point away from positives and field lines go into negatives like so. All right, now this is the version that we are going to be working with. Off to the side, please draw this version as well. So this is a pair of plate that is not infinitely long. Not infinitely long. And what you need to know, once again, the top plate will say it's positive and the bottom plate is negative, is that we have this very special thing that happens on the outside edges of the plates. Okay, and it's called fringing, where the field lines isn't vertical like it is in between the plates, but rather it bows out like so. Bows out like so. Okay, so boom. And because we don't want to be dealing with those kinds of plates, we are going to say that we are dealing with infinitely long plates, or a section of a plate. Okay, now this is what you need to know. The scenario is we are going to be shooting a charged particle through these plates. Okay, and let's say we have a charged positive particle. Actually, we'll make it negative. No, positive? Yeah, we'll make it positive. All right, so right in between these two plates, let's say the separation distance between the plates, we're just going to call it D. And right in between the two plates, smack in the middle, right there, we're going to have a positive charge. Right? And this positive charge will have an initial velocity, and we'll call that just VO. Okay? All right, so let's think about this in a conceptual manner. When this positive charge is moving through the plates, okay, and it's moving right there with a horizontal velocity VO, what is going to happen? Well, because this positive charge is under the influence of an electric field, it'll display characteristics of a charged through electric field, meaning that the positive plate above will push the positive charge down, and the negative plate below will pull the plate in. And so what we get is a path, a parabolic path that looks something like this. Like that. All right. Now, this is very important for us to know because it should remind you of something. Yes, this is exactly what happens with projectile motion. These are horizontal projectile motion equation or scenarios. All right. So, but before we dive back and we do a quick recap of the projectile motion unit, let's go over the new stuff, what we can use in terms of electricity. So first off, we have our equation, F is equal to EQ. Now, it is important to know that for charged parallel plates, the E field is constant. All right, meaning that the E field, let's say up here, the value there versus the value there is constant. Okay, the value here versus the value here, it's constant. The E field, it doesn't change, right? That's something very unique. All right, next thing we need to do is we need to combine Newton's second law with our force equation up here. And Newton's second law says F equals ma. So if I substitute these two in for each other, we get ma is equal to eq. And this will be very important for us, as you'll see in a little bit. So let's do a recap of projectile motion. So projectile motion. First off, the projectile motion formulas, which are on your equation sheet. We have xf is equal to xo plus v initial times time plus 1/2 acceleration times squared. We have final velocity is equal to initial velocity plus the acceleration times the time. And the last one is we have final velocity squared is equal to initial velocity squared plus 2 times the acceleration times the change in position, aka displacement. So here we have our projectile motion equations. But because we're dealing with the x and the y axes, whenever we solve these problems, it is very important for you to create a kinematics table. So kinematics table, you need to have your x and your y. All right, and then we're going to list all the variables that are necessary, such as initial position, final position, initial velocity, final velocity, the acceleration, and of course the time. All right, so here are the table of variables. Now, if you remember from the kinematics unit, there were a couple of things that we said were the same for any given problem, especially for these horizontal motion problems. So let's take a step back away from electricity and go into a like a ball on a cliff, right? So if we have a ball on a cliff and we kick this ball horizontally, because this ball is within a gravitational field, whoa, we're using our new terminology here. That's my gravitational field. What's going to happen is that the ball will move forward, but because it's under the influence of the gravitational field, it'll move in this parabolic path and it'll crash into the earth, right? Just like that. Just like our scenario for the two charged plates. Now, there are a couple of things about the scenario that we knew to be true, such as your initial x velocity and your final x velocity, they're the same. So we can write v initial x is equal to v final x. And we can just call that just vx. Okay, this is true. And that is still true for us. So we can say these two are the same. So we can say, it's going to erase this, and we can write the word same there. All right, these two are the same. Also, we said that at the highest point, our v initial y, because we are at the peak, is 0 meters per second. And that is still true here. We can write that the y initial velocity will still be 0 meters per second. All right. Now, another thing that we said is that because it's under the influence of this gravitational field, we said that the acceleration in the y direction was negative 10 meters per second squared. Negative because it's pointing downwards, right? However, we can't say this. We cannot say that. And that's because we're not under the influence of a gravitational field, right? So we can't write that down. But the other thing, well, that's about it, right? The only other thing is that like our final position, if we're hitting the floor, we usually say that's 0 meters, but we can't really necessarily say that here because it's really dependent on the separation distance of the two charges and the two plates. Oh, one more thing. According to our definition of acceleration, if you remember, acceleration is the change in velocity over a period of time. Right, this is the definition of acceleration. Because the x-axis, velocity final minus velocity initial, right? Because the two are the same, vx minus vx over delta t, this just gives us 0, right? And so our acceleration is 0, and that will be still true for us here. All right. Now, the reason why I had us write this equation up here is because that will help us determine the acceleration in the y-axis. In fact, we can write that out as a is equal to eq over m. All right. Now, the reason why I don't want to put that into the equation chart yet is because I need to think about this, right? So for in this problem here, it just so happens that we have a positive charge. It just so happens that the top plate was positive, and it just so happens that the bottom plate was negative, right? And so it's moving forward, but it's also moving, it's accelerating downwards, right? But this could, easily be flipped. The top charge plate could be negative, the bottom charge plate could be positive, and instead of moving forward and down like this, it could also move up like so, right? This positive charge could have been a negative charge, and in that case, the scenario will also change. And so what I need for you to do is to always sketch these out and to think about your scenario, but just so you know that this equation is there for you to use. All right. Yeah, and the other thing that you need to know is that when we did the projectile motion problems, most of the time we used the y-axis to find time, okay? Because we usually said the time it takes for it to traverse a vertical distance was the total time, right? So like 9 out of 10 times we use the y-axis first, but in case there's the occasion where we use the x-axis, we have to use the x-axis. Another thing that you need to know is the reason why we create this table is when we put the variables in the equation, we can't cross over, right? We can't have x variables and y variables in a single equation. If you're using x variable stuff, you can only use x variable stuff. If you're using y variable stuff, you can only use y variable stuff. All right. Okay. And I think that is about it for the field moving through, or a charge moving through a field. So let's just do a quick little recap. First off, we can find the acceleration, and it is in the y direction by combining F is equal to EQ with F is equal to MA to get A is equal to EQ over M. And the reason why I don't want us to have just that down yet is because that's not in our equation sheet. Right? You'll have to actually combine the two yourself in your brain. All right, next off, these problems are very similar to the projectile motion problems, and in fact they're so similar that they use the same formulas that we use for objects here on Earth. Isn't that cool? The stuff that is works for here on Earth also works for charged particles. Pretty nifty if you think about it. Next, the E field between the two charged plates are the same. Okay, the E field at one point is the same as the E field at a different point. So we can say that the E field is a constant field. It is a constant field. And the only other thing that we can really do is to just get some practice in, right? And so that's what we will be doing in class. I'll see you next time. Bye-bye.